Hey guys, how you doing? So this is 3.4, and I had a student ask me to record these, and so I didn't during class, but I will now. And I also think it's going to be good for some of you to take a look at the later examples, and just for some of the algebra and stuff, so that you make sure that you know what you're doing. So I'm going to break this up into 3 videos. I'll start off with the first one, example 1, and then I'll do example 2, and then I'll do example 3, so the videos don't get too long. Let's see if I can back out here a little bit. Okay. All right, so let's see what we got. What are the possible ways that two lines in a plane can intersect? So remember, language is very important in vectors. We're talking about two lines in a plane. Well, that's not like snakes in a plane. No. We're talking about a two-dimensional plane. We're talking about something like an x and a y axis. The top of your desk can be a plane, and if we think about two lines in your plane, then what can happen is you can have two lines such that they intersect at one point, exactly one point. You could have two lines that don't intersect at a point. They're what we call parallel and distinct. And we could have two lines that are parallel and coincident, meaning that they lie right up on top of each other. They share an infinite number of points. So again, in mathematics, when we talk about the different ways that there can be an intersection, or how many intersections, what we talk about is there could be one intersection. Here's line 1, here's line 2. They intersect here. There could be an infinite number of intersections. Line 1 and line 2 are intersecting everywhere. Or we could be talking about line 1 and line 2 and they're not intersecting anywhere. And not intersecting in mathematics is a form of intersecting. I know, sounds weird, but it's the way it goes. Okay, so using vector mathematics, what can we do here? Determine if the lines intersect, and then determine the point of intersection if one exists. Okay, so the first thing I'm going to do is I'm going to take a look at the direction vectors, because direction vectors are going to tell me whether or not they're going to be parallel, and this could be parallel and this could be parallel. So if I take a look at the direction vectors, and if they're not parallel, meaning that they're not scalar multiples, then I know for sure that I've got one point of intersection. If I take a look at the direction vectors and they are scalar multiples, then I know I've got this situation going on or this situation going on. In which case, what I do is I check for a point of intersection. I'll take the point that's on one of the lines and plug it into the point on the other line. And if it lies on both lines, then this is what we've got. And if the point only lies on one line, then this is what we've got. So once again, listen to that again, because I'm not going to do an example of it. If I take a look at the direction vectors, and if the direction vectors happen to be scalar multiples, then I know that I've either got this situation or I've got this situation. Now what I'm going to do is take the point of one of the lines, either this point or this point. I would set up the parametric equations, plug the other point in, see if the t values is the same for both of those values of the point, and if it works out, then it lies on the line that I plugged it into, it lies on the line that I took the point from, in which case it lies on both lines, and this is our situation. If the t values do not work out to be the same, then we know that the point only lies on the line that we took it from and not on the line that we're plugging it into, in which case this is our situation. Okay, but back to our example. So let's take a look. Check the direction vectors. And I always do this first. It doesn't have to be done first, but I like to do it first. So D1 is going to be 3, negative 2, and D2 is going to be 2, 1. So what I like to do is I like then to try to figure out what it is I would have to multiply 3 by to get 2. Well, to multiply 3 to get 2, I'd have to multiply it by 2 over 3. Spend a moment and think about that and you'll get it. So the question is that if I multiply this by the same value, if I multiply negative 2 by 2 over 3, do I end up with 1? And in fact I do not. I end up with negative 4 over 3. So what this tells me is, it tells me that therefore D1 is not a scalar multiple of D2. That's an important thing to include. I think that we should have that. Is it just me or are things fuzzy on this? I'm going to try focusing it one more time and then we're just going to live with it. All right, I think we're just going to live with it from here on in. So this is what we get, and therefore the lines must intersect at exactly 1 point. Okay, because this is the situation that we've got happening. Okay, so now we want to find the point of intersection. So what we're going to do is we know that there's a point of intersection, and I'm going to change my logic a little bit now, and I'm going to say at any point of intersection, the x value for line 1 must equal the x value for line 2. Also, the y value for line 1 must equal the y value for line 2. Now I could put line 1 down here, and line 2 down here, and line 1 down here, and line 2 down here. But what's important to me is that x equals x and y equals y. We're going to take these and we're going to put them into the parametric equations. So R1 parametrics are going to look like x equals 18 plus 3t1, and y equals negative 2, take away 2t1. And for R2, the parametrics are going to be negative 5 plus 2t2, and y is going to equal 4 plus t2. These are my parametrics. So now if I go ahead and say x equals x per se, so x equals x would be 18 plus 3t1 equals this x, minus 5 plus 2t2. Rearranging this will give me 3t1s, subtract 2t2s, and negative 23, I believe. We're going to call that equation 1. Over here for y equals y, it's going to be negative 2t1 equals 4 plus t2. I'm going to bring this over and bring that over, so it's going to be, let's see, it's going to be 2t1, brought that over, plus t2. This is coming over as negative 6. And there we go. And we're going to call that number 2. Now, what I call these are my elimination equations. Because what we have now are two equations with two variables that I need to solve. I'm just going to fix the camera up a little bit so I can see the bottom of the page. So we set them up for elimination. So it's going to be 3t1 minus 2t2 equals negative 23. And 2t1 plus t2 equals negative 6. I want to set this up for elimination. So in other words, I want the coefficients here or here, I don't care which one, to match up. So I'm going to multiply the bottom one by 2. It's the easiest. And that's going to leave me with is 4t1 plus 2t2 equals negative 12. And on top, we didn't do anything to it, it's 3t1 minus 2t2 equals negative 23. Okay, what we're going to do with this now is we're going to use the process of elimination. So we do a line and brackets. The signs are the same, so we want to add them. What? What are you doing? Well, we're adding. If we take negative 2 t2s and add it to 2 t2s, then what's going to happen is we're going to get 0 t2s. What happens is we get this. 7 t1s plus 0 t2s equals negative 35. These are gone now. That's why it's called the process of elimination, because we eliminate one of the variables. You've got 7t1 equals negative 35. We get t1 equals 5. That's the value when x will equal x and y will equal y. I don't have to go through and find t2. I have enough with t1. All I have to do is go back and plug it in to the appropriate parametrics. I shouldn't be plugging it in here because that would be for t2. Had I solved for t2, I'd plug it in. But I solved for t1. So to get the point of intersection, I'm just going to change colors here. So for point of intersection, sub t1 equals 5 into parametrics of line 1. And so it's going to be x equals 18 plus 3 times 5 It should be -5. I wonder how long people have been yelling at me about that. But it should be -5 here, so a negative goes in here. So it's going to be 18 take away 15, which is going to be 3. And y is going to be -2, -2 times -5. So I guess that will be 8. So our point of intersection is 3, 8. Now, if we want to check and make sure, what we could do is, I guess I'm going to grab a piece of scrap paper, and I'm going to take the second line that we had, its parametrics, which are up here. So it's x equals -5 plus 2t2, and I know that y equals 4 plus t2. This is line 2, and we're going to sub in our point of intersection, which was 3, 8. So we're going to sub that in. And if it works, then that point lies on both lines, and it must be the point of intersection. So you're going to get 3 equals -5 plus 2t2. So it's going to be 8. 2t2 is going to equal 4 here. And if I sub in 8 for y, I get t2, and I get t2 equals 4. Because the t2 is 4 and the t2 is 4, that means that I can get to the point 3, 8 starting at -5, 4 if I utilize 4 direction vectors. So 4 direction vectors will get me to the new point 3, 8, which means that it does lie on this line, and therefore it is the point of intersection between the two lines. There you go. Example 1 done.